We will now consider a few problems, numerical problems related to the PCM system. So this is one problem. Derive an expression for signal to quantization noise ratio for a PCM system which employs linear, that means uniform quantization technique, given that input to the PCM system is a sinusoidal signal. And same problem in different language. A PCM system uses a uniform quantizer followed by a V bit encoder. We will consider it as n because we have already used number of bits as n. So whatever may be, V bit encoder, show that RMS signal to quantization noise ratio is approximately given as 1 plus 6V dV, where V is the number of bits. So let us try to solve this problem. So first we will consider the sinusoidal signal have a peak amplitude of, say, AM. AM is the peak amplitude. So the power of this signal power, that is equal to V square by R, where V is the RMS voltage and V equal to AM by root 2. So m square t bar is equal to m square by 2 into R. So if we consider normalized power, then we set R equal to 1. So m square bar is equal to m square by 2. Now from our previous analysis we have seen that signal to noise ratio can be written as 3 into levels, number of levels square, so L square into m square t bar by mp square, that we have already seen. And also L square means 2 to the power 2V. V is the number of bits for PCM. We have already derived this m square, sorry, m square t bar. So m square by 2 divided by mp square is the peak amplitude am, so m square. So it becomes 1.5 into 2 to the power 2V. So now if we express this SNR in decibel, that is equal to 10 log to give a strain of 1.5 into the power 2V, that is equal to 1.76 into plus 6V, or you can approximately write it as 1.8 plus 6V. So this is in dB. This is also in dB. So that's the answer for this question. Now we will consider another problem, numerical problem. A television signal having a bandwidth of 10.2 MHz is transmitted using binary PCM system. Given that the number of quantization levels is 512 determine the code word length, transmission bandwidth, final bit rate, and output signal to quantization noise ratio. So this is the problem. So let us try to solve this problem. Well, the given value, the bandwidth of the given signal is 10.2 megahertz. The number of levels, say V equal to 512, L equal to 512. This is the FM. Now you know that L equal to 2 to the power V, that is equal to 512. So that implies that V equal to 9. So the bandwidth of this is the answer of question number 1, first question. Code length is 9. Now we have to determine the bandwidth of PCM, transmission bandwidth. So bandwidth is equal to V into FM, that is equal to 9 into FM is 10.2 megahertz. .8 megahertz. So this is the answer of second question. To determine the third question, the final bit rate, we have to first determine the number of samples per second. Assuming we have sampled it at Nyquist rate, then the sampling frequency must be equal to twice of FM. So that is equal to 2 into 10.2 megahertz, 10.2 mega samples per second. That is equal to 20.4 mega samples per second. So this is the number of samples per second, and for each sample we have 9 number of bits. So bit rate is equal to V into Fs, that is equal to 9 into 20.4. Since it is mega sample, so we must have megabit per second. 183.6 Mbps. So this is the answer to the third question. Now you have already determined the expression for SNR in decibel, that is alpha plus 6V. Now alpha can be written as 4.8, assuming the power of the message signal is the peak power allowed, that is m square equal to mp square. So plus 6 into V, it is equal to 4.8 plus 6 into V is 9, 6 into 9. So this is the signal to noise ratio.